Come on, my dears. Last time we had finished theoretical portion of chapter number 2. Today we are going to begin illustrations. Please kindly read the statement of first illustration. Come on, have you read it? Tell me, in the condition of resonance, they have asked resonant frequency, and if only frequency is there, we should write down F0. If series resonant angular frequency is there, then we should write omega 0. Only frequency means F0, angular frequency means omega 0, correct? Right now, series resonant frequency, so I am putting F0. What is the formula for that? 1 upon 2 pi under root of L into C. Come on. 2 as it is, pi value is 3.14, under root of, come on, L. Inductance you are given 8 millihenry. Convert it into Henry, multiply by 10 raised to minus 3. Come on. C. Capacitance they have given 80 microfarad, multiply by 10 raised to minus 6. Convert it into farad. Simplify. Answer is 199. You know unit of frequency is hertz. Symbol is capital H small z. Don't put any full stop. Okay, fine. Now at the time of resonance, tell me, in case of series resonance, at the time of resonance, come on, mod z value becomes minimum, and that minimum value is equal to resistance of a resistor, which they have given 400 ohm. What is IRMS formula? In case of AC circuit, current means RMS value of current, voltage means RMS value of voltage. So according to Ohm's law, current equals to voltage upon resistance. Instead of I, you just write IRMS. Instead of V, you just write VRMS. And instead of R, you just write magnitude of complex impedance of whole circuit. Come on, VRMS value they have given in the statement 230 volt. See, in the statement you will find they have given AC voltage. I told you, in case of AC circuit, only voltage means RMS value of voltage. So RMS value of voltage they have given 230 volt. Mod Z we know it is 400 ohm. This upon this answer is 0.575 ampere. Okay. Let us find out now magnitude of inductive reactance, and that is XL. By formula it is omega L, but you are talking about resonance. In case of resonance, omega equals to omega 0. So I am putting here omega 0. You know formula of omega 0, it is 2 pi F0 into L. Come on, 2 as it is, pi value 3.14. F0, come on, we have found out it is 199 hertz. What about inductance? They have given 8 millihenry, convert it into Henry. Come on, multiply, answer is 10 ohm. Mind well, whether it is resistance or reactance or impedance, all of them are having same unit, that is ohm. Come on. Xc is also 10 ohm because at the time of resonance, come on, XL equals to Xc. Remembered? At the time of resonance, what happens? The imaginary part of complex impedance becomes 0. What was that imaginary part? XL minus Xc. If XL minus Xc becomes 0, meaning thereby XL equals to Xc. So whatever is the value of XL, same is the value of Xc. Correct? Fine. Now they have asked voltages across the components, resistor, inductor and capacitor. Let us find out one by one. Voltage across resistor, according to Ohm's law, it is current into resistance, but in case of AC circuit, current means RMS value of current, correct? So, it is IRMS into resistance of resistor, which is capital R. What about IRMS? IRMS is 0.575. What about resistance? They have given in the statement 400 ohm. This multiplication is 230 volt, correct? What about voltage across inductor? It is again IRMS into resistance provided by inductor. Effective resistance provided by inductor is nothing but magnitude of inductive reactance, which is XL. Come on, IRMS is 0.575 ampere. XL we have found out it is 10 ohm. This multiplication is 5.75 volt. Come on, similarly voltage across capacitor, come on, it is IRMS into XC, IRMS into XC, where XC gives you effective resistance provided by capacitor to the flow of alternating current, and it is also magnitude of capacitive reactance, it is XC. Come on, IRMS is 0.575 ampere, and what about XC? XC is also 10 ohm only, XC is also 10 ohm. This multiplication is 5.75 volt, correct? Now, kindly read this statement of sum number 2. Read it? Look. Please note it very carefully. Here is a circuit in which L and C are connected in parallel, not in series. They are connected in parallel. And then that parallel combination is connected in series with a resistance. See, up till now, we had made the analysis of all 11 AC circuits. Remembered? In that, from circuit number 1 to 9, they had components connected in series. But the last two circuits, remember, the circuit number 10 and 11, in that you are finding L and C connected in parallel. See, there is a difference between condition of resonance in series RLC AC circuit and in parallel LC circuit. There is a difference. Please make it a point. Please remember, in case of series LC circuit, if resonance takes place, then mod Z becomes minimum and current becomes maximum. But in case of parallel LC circuit, the difference is that in case of parallel LC circuit, at the time of resonance, mod Z becomes maximum and current becomes minimum. Please remember. Come on, in this case, in which L and C were connected in parallel, and the parallel combination was connected in series with resistance. In that case, if you have remembered, we had obtained the formula of magnitude of complex impedance, and that formula was mod Z equals to under root of R square plus 1 upon omega L minus omega C whole square. See, this was real part, this was imaginary part, and you know, magnitude of complex impedance is always equal to square root of summation of squares of real and imaginary parts. Okay, fine. Now tell me, because L and C are connected in parallel, at the time of resonance, mod Z should become maximum. So, in order to obtain value of mod Z maximum, tell me from this formula, if you want this value maximum, then this denominator should be made minimum. And minimum value of this denominator, right now you can take 0. If I take minimum value of this denominator, say 0, when this is minimum, come on, this will be maximum. Come on, minimum value of this part is 0, 1 upon omega L minus omega C equals to 0. Just transfer this. When you transfer from minus, it will become plus. Come on, take this omega over here, take this C down, omega into omega, omega square. When you bring this C down, 1 upon L into C, 1 upon L into C. Take square root on both the sides, square root of this is omega. that will give you 1 upon under root of L into C. Mind well, this is the formula for, come on, series, resonant, angular frequency. No, it is not a series connection, it is a parallel connection. So, this is the formula of angular frequency at the time of resonance in case of parallel LC circuit. In case of parallel LC circuit, same formula was there for series AC circuit also. So, whether it is series AC circuit or parallel AC circuit, so far formula of resonance frequency is concerned or resonant angular frequency is concerned, formula is same. Okay, omega equals to 1 upon under root L into C. But remember, once again I am reminding, in case of parallel LC circuit, at the time of resonance mod Z becomes maximum, and that maximum value here it is infinity. Why? Because when this part is 0, 1 upon 0 will be infinity, infinity square infinity, infinity plus something infinity, square root will be infinity. So, mod Z will become infinite. When mod Z becomes infinite, what is the formula of IRMS? Formula of IRMS is VRMS upon mod Z. Here it is, IRMS equals to VRMS upon mod Z. At present, mod Z is infinity, put it here. Something upon infinity will become 0, correct? Fine. Now, read the statement of number 3. Come on. They have given two equations. One is of voltage, another is of current. Voltage equation is this: 200 root 2 cos of 3000 t minus 55 degree, that many volt. Current equation is 10 root 2 cos of 3000 t minus 10 degree, that many ampere. And now suppose I require phase difference between current and voltage. If you require phase difference between current and voltage, you can find it this way. Look, this bracketed part with this cosine function in the formula of current will give you phase of current. How much? 3000 t minus 10 degree, 3000 t minus 10 degree, minus phase of voltage. Similarly, phase of voltage is how much? 3000 t minus 55 degree. Come on, 3000 t minus 55 degree, correct? This is phase of current minus phase of voltage. At present, you know what we have done? We have taken greater phase minus smaller phase. Come on, find the value of delta. It is this minus this. 3000 t minus 3000 t will cancel. Minus minus plus 55 degree minus 10 degree. 55 degree minus 10 degree, that is 45 degree, correct? Now, recall the formula of tan delta. What was tan delta formula? XL minus XC upon R. Come on. Now, right now delta is 45 degree, put it here. Put it here, tan 45 degree. Tan 45 degree is 1. That is why tan delta written equal to 1. Transfer this. So, it is XL minus XC equals to R. XL minus XC equals to R. Recall formula of mod Z. What was that formula? Under root of R square plus XL minus XC whole square. Come on, under root of R square plus XL minus XC whole square. In place of XL minus XC, we can write R. So, in place of XL minus XC, if you write R, so it is now under root of R square plus R square. Under root of R square plus R square means under root of 2R square. Under root of 2R square means what? Root 2 into R. Give it equation number 1. Now, recall the formula of maximum current. Im equals to Vm upon mod Z. Im equals to Vm upon mod Z. How can you get it? Remember this formula? IRMS equals to VRMS upon mod Z. Tell me, what is IRMS? Im upon root 2. What is VRMS? Vm upon root 2. So, from both the sides, 1 upon root 2 will be getting cancelled, giving you Im equals to Vm upon mod Z. Correct? Fine. What is Im value? See, you can read this equation this way, I equals to Im cos of omega t minus delta. So this is Im. Maximum value of current is right now 10 into root 2. Maximum value of current is 10 into root 2 ampere. What about similarly maximum value of voltage? V equals to Vm cos of omega t minus delta. So this gives you maximum value of voltage. The coefficient of this cosine function will give you here maximum current, and here coefficient will give you maximum voltage. It is 200 root 2. This maximum voltage is 200 root 2 mod z as it is. Okay, simplify, root 2 getting cancel. Mod z you can take up, 200 upon 10, that is 20 ohm. Correct? Fine. Now from equation number 1, just put mod z equal to 20 ohm. Mod z equals to 20 ohm, put it here. Mod z is 20. This root 2 as it is into R. And now tell me, what is the value of R from here? You will get this value 14.14, that many ohm. Here, some of you might be thinking that this delta is actually phase difference between voltage and current. Voltage and current. So you should take phase of voltage first minus phase of current later on. If you do that here, then you should take this phase minus this phase. And if you take this minus this, then delta value will come out minus 45 degree. Delta value will be minus 45 degree. And if delta is minus 45 degree, then tangent of minus 45 degree comes out to be minus 1. So here it is minus 1. And in that case, XL minus XC will be minus R. XL minus XC will be minus R. Multiply on both the sides by minus 1, then you get XC minus XL equal to R. XC minus XL equal to R. And in the formula of mod Z, whether here you write XL minus XC or you write XC minus XL, it makes no difference, correct? And then ultimately square will be positive. So whether it is XC minus XL or XL minus XC, whether here it is plus R or minus R, ultimately you will get under root of R square plus R square only. So that is root 2 into R. So final answer will remain same, correct? But actually let me tell you, this delta is phase difference between voltage and current, between voltage and current. So you should take phase of voltage first minus phase of current later on. Got it? Come on, read now statement of sum number 4. Read it. We are given some typical current which has two components. One component is DC, another component is AC. And when you make algebraic addition, is going to give you resultant current. So let it be I equals to IDC plus IAC. What is IDC? Come on, it is constant, it is 12 ampere, and IAC they have given 9 into sine of omega t. Fine. Now we are asked to find out RMS value of this current. The shortest, the easiest way to find out RMS value is this. Just make square on both the sides. So here you can write now I square. If it is A plus B, suppose A plus B, and then you are making square, A plus B whole square, how much it is? A square plus 2AB plus B square. Okay. So square of first term, square of 12 is 144 plus 2 times first term into last term. 2 into 12, that is 24 into 9, it is 216 sine of omega t, and plus square of last term, square of this will be 81 sine square omega t. Come on, 81 sine square omega t. Got it? Now just take average in all the terms. Average in all the terms. When you take average here, you can write average of I square, but 144 is a constant value. There cannot be any average. Whenever any constant term is there, you just leave it as it is. Come on. 216 also as it is. Average of this, I have written here, average of sine of omega t plus 81 is constant, average of sine square omega t, average of sine square omega t, okay. 144 as it is, 216 also as it is. Remembered earlier I told you in chapter number 1, average value of sine or cosine function over one periodic time is 0. So average value of sine function over one periodic time is 0. So this part is 0, correct. 81 as it is. But now tell me, average of sine square, average of sine square. Remember one more result. If it is average of sine square or cos square over one periodic time, it is 1 by 2. It is 1 by 2. Average of sine square or cos square over one periodic time is 1 by 2. Please remember. So this average value, we know it is 1 by 2. Now just simplify. This part is 0 and 81 upon 2, it is 40.5, 40.5. Plus this, answer is 184.5. And now take square root on both the sides. Square root here also, square root here also. Come on, under root of average of I square, here under root of 184.5. Now what is this? Root mean square current. Root mean square current, that is IRMS. And square root of this comes out to be 13.58, that many ampere. Okay. Now read the statement of number 5. Come on, read it. See, we are asked to find out the equivalent inductance out of parallel combination of two inductances. How to find? I am showing you. Look, if ZL1 is the inductive reactance of first inductor, ZL2 is the inductive reactance of second inductor, and then if you are connecting them in parallel, and if the equivalent inductive reactance is ZL, then according to law of parallel combination of inductors, 1 upon ZL equals to 1 upon ZL1 plus 1 upon ZL2. Fine. According to law of parallel connection of inductive reactances, 1 upon ZL equals to 1 upon ZL1 plus 1 upon ZL2. Come on, ZL is equivalent inductive reactance, that you can write J omega L, where L is equivalent inductance. ZL1 is, come on, J omega L1, ZL2 is J omega L2. Throughout the equation, what you can cancel? 1 upon J omega, 1 upon J omega, 1 upon J omega you can cancel. So left is 1 upon L equals to 1 upon L1 plus 1 upon L2. Find out L value from here. It will be L1 L2 upon L1 plus L2. Multiplication upon addition. Okay. But mind well, this formula which you are writing, a multiplication upon addition, L1 into L2 upon L1 plus L2. Don't write multiplication upon addition in case of parallel connection of more than two inductors. Don't write so. See, if it is more than 2, suppose 3 are there, then from here 1 upon L will be equal to 1 upon L1 plus 1 upon L2 plus 1 upon L3. In that case, you will get L equals to L1, L2, L3. But in the denominator, it is not L1 plus L2 plus L3. No, L1, L2 plus L2, L3 plus L3, L1. Okay, so take care. Don't remember this as a general formula. Remember this as a general formula. 1 upon L equals to 1 upon L1 plus 1 upon L2 plus 1 upon L3 plus dash dash dash, depending upon number of inductors, okay, connected in parallel. This you can apply only for, come on, parallel connection of only two inductors, okay. At that time you can write L1 into L2 upon L1 plus L2, that is multiplication upon addition, okay, fine. Read now number 6. Read it. Look, we are given an AC circuit in which L and C are connected in series, and that series combination is connected in parallel with resistance, and across this circuit one AC source is connected. In this case, we are asked to find out formula of magnitude of equivalent impedance, formula of magnitude of equivalent complex impedance. Let us find out. First of all, think about inductive reactance provided by this inductor. It is ZL equals to J omega L. Capacitive reactance formula is ZC equals to minus J upon omega C. Correct? This R as it is, fine. And now tell me, take this R as Z1. Take this R as Z1. So instead of R, I am just putting new symbol Z1. And instead of series combination of L and C, I am just putting equivalent reactance as Z2. Then Z2 will be ZL plus ZC because it is a series combination. ZL plus ZC. Here it is ZL plus ZC. But ZL is J omega L, ZC is minus J upon omega C. When you want to make addition, ZL plus ZC, it will be this plus this. And in that, you can take J common. Inside the bracket, omega L minus 1 upon omega C. Omega L minus 1 upon omega C. Correct? Come on, J as it is. What is omega L? Omega L is nothing but magnitude of inductive reactance, to be shown by symbol XL, minus 1 upon omega C is magnitude of capacitive reactance. It is XC. Fine. Now tell me, this is Z1, this is Z2. Because they are connected in parallel, according to law of parallel connection of, come on, impedances. According to law of parallel connection of impedances, 1 upon Z, if Z is the equivalent impedance, then 1 upon Z equals to 1 upon Z1 plus 1 upon Z2. Correct? Z1 is R, Z1 is R, and Z2 is J into XL minus XC. Z2 is J into XL minus XC. Come on. Just write in place of plus 1, in place of plus 1, you can write minus J square. In place of plus 1, what you can write? Minus J square. So here I am writing minus, and here J square upon J. J square upon J, so J will be left in the numerator. And now, if you associate this negative sign inside, correct, then order will be reversed. 1 upon XC minus XL, 1 upon XC minus XL. And this J is there in multiplication, I have written here, fine. I have taken this negative sign inside, so order is getting reversed. So plus J into 1 upon, order is reversed, XC minus XL. Now take magnitude on both the sides. 1 upon magnitude of Z I have written here. And now this is the complex number in which without J this is real part and coefficient of plus J is imaginary part. And you know, magnitude of any complex number can always be written as square root of summation of squares of its real and imaginary parts. Fine. Now under root as it is, correct? Take LCM, R square into XC minus XL whole square, that will be LCM, multiply here by XC minus XL whole square, multiply here by R square, correct? And now take reciprocal. When you take reciprocal, it will be here mod Z, and here when you take reciprocal, the denominator part will become numerator, numerator will become denominator. So it is under root of R square into XC minus XL whole square upon R square plus XC minus XL whole square. Okay. Now at the time of resonance, tell me, because L and C are in series, at the time of resonance, mod Z should become minimum. And here mod Z you can take 0 because at the time of resonance we know XL equals to XC. When you put XL equals to XC here, this part will be 0. 0 upon anything will be 0. Its square root is also 0. So mod Z right now can be 0 at the time of resonance. Okay. Read now number 7. Read it. Look. We are given an AC circuit in which L and R are connected in series, and with that series combination, come on, capacitor is connected in parallel. For such a circuit, we are asked to find out the expression of a resonant frequency. Resonant frequency. What is that expression? I am showing you. Look, take this as Z1. Then because it is capacitive reactance, formula is Zc equals to minus J upon omega C. This I am taking as Z1 minus J upon omega C. And the series combination of these two I am taking as Z2. It is R plus J omega L. Z2 equals to R plus J omega L. This is Z1 and this is Z2. They are connected in parallel. So according to law of parallel combination of impedances, come on, if equivalent impedance is Z, then 1 upon Z equals to 1 upon Z1 plus 1 upon Z2. Come on, what is Z1? Z1 is minus J upon omega C. Z1 is minus J upon omega C. Denominator will become numerator. 1 upon Z2. Come on, 1 upon Z2. Z2 is how much? R plus J omega L. Come on, Z2 is R plus J omega L. Correct? And now tell me, this minus 1 means what? Minus 1 means J square. So it is now J square upon J. J square upon J. So 1 J is there in the numerator multiplied with omega C, J omega C. I repeat, minus 1 is J square upon J, that is J into omega C. And now R plus J into omega L in the denominator I have written as it is. And you know complex conjugate of this. What is complex conjugate number of this? It is R minus J omega L. And with that complex conjugate, I have multiplied in the numerator also, in the denominator also. Okay, fine. This part as it is. Come on, R minus J omega L as it is. But you know, A plus B into A minus B, how much it is? A square minus B square. Similarly, R plus J omega L into R minus J omega L will be R square minus J square omega square L square. I repeat, R square minus J square omega square L square. But you know minus J square is plus 1. So it is R square plus omega square L square. Okay, fine. And now take LCM. This part will appear in the denominator. R square plus omega square L square. And with this you can multiply here. Come on, multiply this with this. J omega C R square. J omega C R square. Multiply this with this. Come on, J omega into omega square, omega cube L square into C plus R minus J omega L plus R minus J omega L. Correct? And now take reciprocal. If you take reciprocal, here it will be Z. When you take reciprocal, the denominator will become numerator, numerator will become denominator. Correct? But this part is going to become now denominator. I have written here, look, R. Correct? Now from these three terms I am taking J outside. Left inside the bracket from here it is omega C R square. Omega C R square. Left inside the bracket from here, when you taken J out, left is omega cube L square C. Omega cube L square C. And because J you have taken out, left inside the bracket from here it is minus omega L. Minus omega L. Correct? Now tell me, how do you find this L and C? In series or in parallel? In parallel. Correct? Remember, I told you, whenever L and C are in parallel, then at the time of resonance, mod Z should be made maximum. In order to make the maximum value of Z, in order to maximize the value of Z, you should make this denominator minimum. But here R is constant, and yet you want this denominator minimum, then this coefficient of plus J, that is this much, you should make minimum, that is 0. Correct? When you make this much part say 0, that is minimum. When this becomes minimum, Z value will become maximum, and then resonance is said to have taken place. Correct? Come on, this part you should take 0. Come on, omega C R square, omega C R square plus omega cube L square C plus omega cube L square C minus omega L should be taken equal to 0. Fine. Now omega C, if I take common, left inside the bracket from here it is R square, omega into c has gone out. So left is omega square L square, and minus if you transfer here will become plus omega L. And now just find out r square plus omega square L square from here. Come on, omega will cancel, omega will cancel, take this c down, so it is L upon c, correct? So subject of the equation is now r square plus omega square L square, it is L upon c. Find out omega square L square, transfer this, from plus it will become minus, correct? And divide each term by L square. When you divide by L square, here it is omega square. When you divide by L square, come on, 1 L will be getting cancelled, left is 1 upon LC. Divide by L square here also, so it is minus r square upon L square. Because I want formula of omega, I should take square root on both the sides. Square root of this is omega, square root of this is under root of 1 upon LC minus r square upon L square. But mind well, this is formula of angular frequency at the time of resonance. Formula of angular frequency. If they ask only frequency, then you are supposed to derive the expression of f, and you know omega equals to 2 pi f. Right hand side as it is, find out f, transfer this 2 pi. So f equals to 1 upon 2 pi under root of 1 upon LC minus r square upon L square. Got it? Come on my dears, read this statement of illustration number 8. Come on, read it. Tell me, in the first case, can we write formula IRMS equals to VRMS upon mod Z? But instead of IRMS, just for the sake of convenience, I have written I. Instead of VRMS, again for the sake of convenience, I have written capital V. But IRMS equals to VRMS upon mod Z. Right now they have talked about series RC circuit. Inductor is not there. So XL is 0. You know mod Z formula, under root of R square plus XL minus XC whole square. Put XL equal to 0. You will get it under root of R square plus XC square. Under root of R square plus XC square. Correct? Fine. Now in the second case, what have they done? Instead of omega, they have reduced angular frequency to omega by 3, and thereby it so happens that current becomes half of the initial value. Initial value was I, now it is I by 2, but current becomes half. Tell me when omega reduces to omega by 3. So instead of omega, you are supposed to write omega by 3. Write it here. So when you write, instead of omega, when you write omega by 3, it will be omega square upon 9. Denominator will become numerator. So 9 will appear here. Correct? Fine. Now this V as it is, under root of R square as it is, 9 as it is. But what is 1 upon omega C? Do you know? It is XC. So 1 upon omega square C square will be XC square. Fine. Now just take the ratio. Ratio of this to this will be equal to this upon this. When you take this upon this, I will cancel. Denominator will become numerator. So 2 will go in the numerator. And when you take this upon this, come on, V will cancel. And this term will appear in the numerator. So under root of R square plus 9XC square upon R square plus XC square. Take squares on both the sides. Square of this is 4. When you take square, square root will vanish. R square plus 9XC square upon R square plus XC square. Just take this part over here. So just multiply 4R square plus 4XC square equals to r square plus 9x square. Transfer this r square here. So, it is 4r square minus r square, that is 3r square. Transfer this part over here, 9x square minus 4x square, that is 5x square, correct. Now, find out x square upon r square. X square upon r square will be 3 upon 5. And now, take square root. So, it will be xc upon r, and when you take square root here, under root 3 upon 5, correct. And mind well, it is right now asked the ratio of, come on, capacitive reactance to resistance. In the examination, they may ask inverse ratio, they may ask r upon xc, at that time it will be under root of 5 by 3, okay. And tell me, what is the unit of reactance? Ohm. Unit of resistance is also ohm. Ohm upon ohm will cancel. So, this answer is unitless, okay. Now, read number 9. Come on, have you read it? We are given voltage which changes periodically with time according to this square type of wave, okay. Now, in textbook, here they have shown solid vertical lines, right. I do not agree with them, because here it cannot be so many values of voltage for the same instant of time. No, it is wrong. Actually, you must show dotted lines. So, do not show here solid lines, show dotted lines, fine. Now, what does this voltage wave shape indicate? It indicates that between 0 to t by 2, voltage is equal to Vm is equal to 100 volt, and that remains constant. Between t by 2 and t, again voltage value remains equal to minus Vm equal to minus 100 volt constant. This is plus Vm, this is minus Vm, this is plus 100, this is minus 100 volt, correct. 0 to t by 2, it is Vm equals to 100 volt, and t by 2 to t, it is minus Vm equals to minus 100 volt constant. Now, if this is the voltage waveform, then what is the RMS value of this voltage? That is what we have to find out, okay. First of all, let us find out average of V square. If you get it, then later on we will take square root, so that we will get V RMS. First of all, let us find out average of V square over one periodic time. So, I should take integration 0 to capital T V square dt divided by capital T. 1 upon t, I just keep it outside. Integration as it is, V square dt as it is. I just split this integration from 0 to t into two parts, 0 to t by 2 and then t by 2 to t. Come on, 0 to t by 2 and t by 2 to t, fine. Now, tell me 1 upon t as it is, integration as it is, V square, come on, take square here, V square will be Vm square, V square equals to Vm square dt plus integration from t by 2 to t by 2 to t, but V is in this time interval, what is the value of V? Minus Vm. So, instead of V, I am putting minus Vm whole square dt, fine. Now, this Vm square is constant, taken out, integration 1 dt, integration 1 dt. Come on, here it is plus Vm square, which is also constant, taken out, integration 1 dt, integration 1 dt. Here limits are from 0 to t by 2, here limits are t by 2 to t by 2 to t. Now, because Vm square is constant, can be taken out, then Vm square upon t, correct. Now, tell me, Vm square has gone out, integration from 0 to t by 2 and again from t by 2 to t. Come on, you can now add them, integration from a to b plus integration from b to c, you can always add integration from a to c. Similarly, here integration 0 to t by 2 plus integration t by 2 to t, correct, for the same function. Come on, you can write it integration 0 to t 1 dt. Now, tell me Vm square upon t as it is, Integration 1 dt is nothing but small t from 0 to capital T, 0 to capital T. Now, this part as it is, instead of small t, you are supposed to write upper limit. After putting minus sign, you are supposed to write the lower limit, that is 0. Now, tt will cancel, giving you Vm square. Take square root on both the sides. Square root of this is under root of average of V square. When you take square root here, it is Vm. And now, this is nothing but, come on, root mean square voltage. Root means square voltage. By symbol, it is Vrms. And Vm is how much? Vm is nothing but 100 volt. So, right now RMS value of the voltage in this case, it is coming out to be 100 volt, correct? Read now statement of sum number 10. Come on. For LC circuit, the series resonant frequency or even parallel resonant frequency, it is same. F0 equals to 1 upon 2 pi under root of L into C. In textbook, same resonant frequency, they have shown by symbol only small f, no problem. Whether you write f or f0, the interpretation remains same. It is right now resonant frequency. Fine. Now take square. So f square will be 1 upon 4 pi square. When you take square, square root will vanish, giving you LC. Now we want capacitance value, so make it subject of the equation. Transfer this f square in the denominator. And now tell me, we are given range of frequency from 800 kilohertz to 1200 kilohertz. So in this range from 800 to 1200 kilohertz, naturally 1200 kilohertz is maximum. 1200 kilohertz is maximum. So when you write here frequency value maximum, you are supposed to get capacitance minimum. That's why I am writing C minimum, and here I am writing F maximum, correct? Come on. 1 as it is, 4 as it is, pi value is 3.14. This inductance is 100 millihenry, convert it into Henry, multiply by 10 raised to minus 3. What about maximum frequency? From 800 to 1200 kilohertz, so 1200 is maximum, but 1200 kilohertz, you must convert into hertz. Come on, multiply by 10 raised to 3 and then square of it, okay? Simplify. Answer is 0.176 into 10 raised to minus 12 farad, but 10 raised to minus 12 farad is nothing but 1 picofarad. So, this is 0.176 picofarad, correct? Now, tell me, instead of F, if I write F minimum, naturally I will get C, instead of C I will get, come on, C maximum. When you write here minimum value, naturally this value will be maximum, C maximum equals to 1 upon 4 pi square into L into F minimum square. Come on, dictate me the values. Come on, pi value is 3.14. Inductance 100 millihenry, convert it into Henry, multiply by 10 raised to minus 3. Come on, minimum frequency in the given range is 800 kilohertz, convert it into hertz, multiply by 10 raised to 3, square of it, okay? Simplify, answer is 0.7 into 10 raised to minus 12 farad, but 10 raised to minus 12 farad is nothing but 1 picofarad. So, this is 0.7 picofarad, correct? So, what will be the range? Range is always to be mentioned. Range is always to be mentioned from minimum value to maximum value. Among these two values of capacitances, come on, this and this. What is the minimum value? Minimum value is this 0.176 picofarad to, come on, what is the maximum value? Maximum value is 0.7 picofarad. From 0.17 picofarad to 0.7 picofarad. That is the range of capacitance required, okay? Fine. Now, read this statement of sum number 11. Come on. What is given to us? Parallel combination of resistance and inductive reactance connected across some alternating voltage source. Fine. We are asked to find out two values. One is the RMS value of current passing through the circuit and another is phase difference between voltage and current. Let us find out. Tell me how to find these two components connected in parallel. For the components connected in parallel, don't you know potential differences would be equal or voltages would be equal. What is voltage across this resistance? It is current into resistance. Come on, current through resistance I am showing by symbol IR. Similarly, what is voltage across inductor? It is current through inductor multiplied by magnitude of inductive reactance, which is XL. Now, these two voltages must be equal because these two components are connected in parallel. Fine. Now, find out IR from here, it will be V upon R. IR equals to V upon R. Find out IL, it is V upon XL. V upon XL. Now, tell me, because these two components are connected in parallel, voltages would be same, and whichever quantity is same, that quantity should be shown by a phasor along positive x-axis. Come on, this is positive x-axis. So, voltage phasor I am showing along positive x-axis because voltage is across resistor and inductor are same. Now, so far current passing through resistor is concerned, you know it oscillates in same phase with the voltage. That is why its current phasor must be shown in the same direction. And so far current passing through inductor is concerned, it is lagging behind in phase as compared to voltage by amount pi by 2 radian. Because it is lagging behind by pi by 2 radian, it must be shown along negative y-axis. Okay. Now, shift this vector from here to here, correct? This phasor I am shifting from here to here. Now, tell me, vector plus vector will give you resultant vector. Here, phasor plus phasor will give you resultant phasor. And so, I is nothing but resultant current phasor, resultant current phasor. And now tell me, because it appears opposite to right angle, it must be hypotenuse, and for hypotenuse, you can just apply Pythagoras theorem to find its magnitude. Come on, I square will be IR square plus IL square. I square will be IR square plus IL square. I square as it is. But what is IR square from here? What is IR square? V square upon R square. Here it is, V square upon R square. What is IL square? IL square will be V square upon XL square. V square upon XL square, correct? Take V square common. V square common. Inside the bracket 1 upon R square plus 1 upon XL square. 1 upon R square plus 1 upon XL square. Take square root on both the sides. Square root of this is I. Square root of this is V under root 1 upon R square plus 1 upon XL square. Fine. This is the required formula for total current passing through this parallel circuit. Fine. Let me tell you, this is the RMS value of voltage, this is the RMS value of current. Okay. Now, tell me what will be tan delta. This is voltage phasor, this is resultant current phasor. So, this angle would give you phase difference between voltage and current. Let it be delta. In this right angle triangle, you just find out tan delta. So, what will be tan delta? Opposite upon adjacent. Opposite to delta, it is IL. Adjacent to delta, it is IR. So, it is opposite upon adjacent, IL upon IR. Now, tell me, tan delta as it is, what is IL? IL is V upon XL. IL is V upon XL, right? IR, what is IR? It is V upon R. V upon R. V will cancel. Denominator's denominator will become numerator. XL will come down. R upon XL. R upon XL. If tan delta equals to R upon XL, what is delta? Tan inverse of R upon XL. Tan inverse of R upon XL. What is the delta? Phase difference between voltage and current. Got it? Now read the statement of sum number 12. Come on, read it. What is the difference between this circuit and this circuit? Correct? They are quite similar, only one difference is there. Here capacitor is not there, here capacitor is added in the circuit. Capacitor is added in the circuit. Okay, now tell me, how do you find these three components? 1, 2, 3 connected in parallel. For the components connected in parallel, voltages are equal. What is the voltage across resistance? Come on, current into resistance, that is IR into R. What is voltage across inductor? IL into XL. IL into XL. What is the voltage across capacitor? IC into XC. Got it? Come on. What is XC? Capacitive reactance? No. Magnitude of capacitive reactance. What is XL? Inductive reactance? No. Magnitude of inductive reactance. Got it? Fine. Find out IR from here. It will be V upon R. IR equals to V upon R. IL equals to V upon XL. And IC equals to V upon XC. V upon XC. Got it? Now let us show all the required quantities in the phasor diagram. Here, because these components are connected in parallel, voltages are same. Whichever quantity is same, its phasor you must show along positive x-axis. Right now voltage is same, so voltage phasor we just show along positive x-axis. Now so far current passing through capacitor is concerned, you know it is leading ahead in phase by amount pi by 2 radian, so it must be shown along positive axis. And so far current passing through inductor is concerned, it is lagging behind in phase by amount pi by 2 radian, so it must be shown along negative y-axis. Suppose IL is greater than IC, suppose, then bigger minus smaller. If you take IL minus IC, you will get it this way. Suppose this much phasor is IL minus IC, and now this phasor I just shifted from here to here, correct? Fine, this is now IL minus IC. Now phasor plus phasor will give you resultant phasor, so I is nothing but resultant current phasor. Now this is voltage phasor, this is current phasor, this is the common phase difference between them. And now because this appears opposite to right angle, it will be hypotenuse, and according to Pythagoras theorem now I square will be IR square plus IL minus IC whole square. I square will be IR square plus IL minus IC whole square. Come on, what is IR square? IR square from here, come on, IR square will be, come on, V square upon R square, V square upon R square plus IL. What is IL? V upon XL, V upon XL minus what is IC? IC is V upon XC, V upon XC whole square. Now V square I can take out from the right hand side. See, when you take this V and this V common, after making it squared you can take it out. But that V square and this V square totally can be taken out from the right hand side. Left inside the bracket from here is 1 upon R square, 1 upon R square plus 1 upon XL minus 1 upon XC whole square. 1 upon XL minus 1 upon XC whole square. Take square root on both the sides. Here square root will be I, here square root will be V, and here under root of 1 upon R whole square plus 1 upon XL minus 1 upon XC whole square. Now tell me, this is the required formula for resultant current. Let me tell you, this gives you RMS value of current, this gives you RMS value of voltage. Fine. What about tan delta? In this right angle triangle, find out tan delta. Opposite to delta divided by adjacent to delta. IL minus IC upon IR. Opposite upon adjacent. IL minus IC upon IR. What is IL? IL is V upon XL. IL is V upon XL minus what is IC? V upon XC. V upon XC. What is IR? IR is V upon R. Come on, IR is V upon R. V can be taken common from the numerator, will be getting cancelled with this V in the denominator, and denominator's denominator will become numerator, so R will go up. So tan delta equals to R into bracket 1 upon XL minus 1 upon XC. Find out delta now, it will be tan inverse of R into 1 upon XL minus 1 upon XC. This gives you required expression for finding phase difference between voltage and current in the given circuit. Got it? Now read number 13. Come on, read it. We are asked to prove that total energy in LC circuit under ideal conditions remains constant. Let us prove. See here, ideal conditions means we assume that no energy is emitted outside the circuit. Okay, the circuit energy remains in the circuit only, and how it remains constant with time, that is what we have to prove theoretically. Look, I am showing you. First of all, find electrostatic potential energy stored in the electric field between the charged capacitor plates. You know its formula, U equals to 1 by 2 Q square upon C. U equals to 1 by 2 Q square upon C. Come on, 1 upon 2C taken by side, and Q square. What was the formula of Q? Q equals to Q0 cos of omega 0 t. It's a square. Now tell me, 1 upon 2C as it is, Q0 square I have written here, cos square omega 0 t, cos square omega 0 t. Similarly, what is the energy stored in the magnetic field in the inductor carrying some current? You know magnetostatic potential G formula, UB equals to 1 by 2 Li square. Come on, 1 by 2 L, what was the formula of I? We had derived minus Q0 omega 0 sine of omega 0 t, and it's a square. Now come on, 1 by 2 L as it is, what about square of this? It is now Q0 square omega 0 square, Q0 square omega 0 square, sine square omega 0 t. Now tell me, 1 by 2 L Q0 square as it is, what is omega 0 formula? Only omega 0 means 1 upon under root LC, but omega 0 square will be 1 upon LC. Omega 0 square will be 1 upon LC into sine square omega 0 t. Now this L and this L will cancel, giving you Q0 square upon 2C. Q0 square upon 2C sine square omega 0 t. Now if we want to find out total energy stored in the entire LC circuit, then U equals to UE plus UB. Come on, UE plus UB means it is this plus this. So come on, Q0 square upon 2C, Q0 square upon 2C. Come on, we can take common inside the bracket, cos square omega 0 t plus sine square omega 0 t. Cos square omega 0 t plus sine square omega 0 t, it is 1, and 1 into this will be same only. So it is Q0 square upon 2C. Because Q0 is constant, because C is constant, this right hand side and hence left hand side does not depend on time. When it does not depend on time, with respect to time, it will remain constant. Time invariant, you can say, time invariant. Okay, thank you. Come on, my dears, read this statement of exercise sum number 14. Come on, read it. I am mistaken. Read this statement of illustration number 14. Read it. Look. You know the formula of power factor in case of series RLC AC circuit. We had drawn phase diagram, and in that there was a right angle triangle, and in that right angle triangle, if you find out value of cos delta, the formula is adjacent side divided by hypotenuse. Adjacent side was R and hypotenuse was magnitude of complex impedance. So cos delta equals to R upon mod Z. Cos delta equals to R upon mod Z. Now tell me R as it is. What about mod Z? For series RLC AC circuit, what is the modulus of complex impedance? It is under root of R square plus XL minus XC whole square. Fine. Under root of R square plus XL minus XC whole square. But what is XL? It is omega L minus XC is 1 upon omega C whole square. Now here all the values are given except capacitance C, which we have to find out. What is cos delta? See, only delta means phase difference between voltage and current. But when I am asking for cos delta, its name is power factor. And what is the power factor given to you in the statement? 0.5. This resistance is given to you 100 ohms. Come on, this resistance is 100 ohm. This angular frequency you are given 100 radian per second. Inductance is 5 Henry. This angular frequency is 100 radian per second. And capacitance, leave it as it is. We require to find it out. Now just simplify carefully. Find out the value of capacitance. You will get it 30.6 into 10 raised to minus 6 farad. But you know very well 10 raised to minus 6 farad is 1 microfarad. So it is 30.6 microfarad. Correct? Now read illustration number 15. Come on, read the statement. Tell me, what was the transformation ratio? It was shown by symbol small r. It was ratio of total number of turns in secondary coil to total number of turns in primary coil. It was Ns upon Np, and right now that transformation ratio you are given 10. Now you know the formula, Es upon Ep equals to Ns upon Np. Es is voltage in secondary coil or output voltage. Come on, Ep means voltage in primary coil or input voltage. Fine. Come on, Es we require to find out. Value of Ep, they are given 110 volt. Come on, Ns upon Np, that whole ratio you know it is 10. Find out Es from here, it is 110 into 10, that is 1100 volt. Let me tell you, this is RMS value of voltage. And from this, if they ask peak value, then you know Vrms equals to Vm by root 2. So if this much is Vrms, then Vrms equals to Vm by root 2. You can find out Vm, that is called peak voltage. Fine. Now for ideal transformation, for ideal transformer, there is no wastage of energy. Hence, whatever is input power, same is output power. What is output power? It is Es into Is. What is input power? It is Ep into Ip. Come on, Es, come on, Es we have found out 1100 volt. Is they have given 10 ampere. That Ep, that is voltage in primary, they have given 110 volt. Ip, current in primary coil, we require to find out. Find out Ip from here, you will get it 100 ampere, 100 ampere. Now once again I repeat, for ideal transformer, there is no wastage of energy, no loss of energy. Hence, whatever is input power, same is output power. Input power equals to output power. Input power is Ep into Ip. Output power is Es into Is. Both of them are same. Es is 1100 volt. Is is 10 ampere. Ep is 110 volt and Ip is 100 ampere. Both the multiplications are same, giving you answer 11,000 watt. 11,000 watt. Thank you.